Hello there, everyone. We are going to take a little journey into some forces today and how to deal with them, what to do with them. I am a trained professional, so hopefully you'll learn at least a little something here. Don't try this at home without some severe and intense training. So hopefully this will get you on your way. Just to start with, we have here what we determined in the last couple days, that the force of gravity on an object is equal to the slope, again, the slope you found in that lab with your graph of force of gravity versus mass. So at 10 newtons for every kilogram times the mass of an object, it will tell you it's the force of gravity that's experiencing. So this is key to what we're going to be doing, as well as a few other things. So some of the classes yesterday got to this diagram, at least. Some of you did not. So I'll just start back at the beginning. I have here a 5 kilogram object hanging from a string from what we would call a rigid support. At this point, what I want to do is look at what a summation of forces will look like. But before we can do that, we need to figure out what the force diagram looks like. So again, we will represent the object. And again, sometimes, it's nice to circle the object because that is the system that we're dealing with. So that is our system, the ball that's hanging by the string. And so in the downward direction, we have the force of gravity on the ball. And again, this is the agent-object way to name forces. Force of gravity. Gravity is the agent of the force. On ball, ball is the object of the force. So agent-object naming is what this is called. So we have the force of gravity on the ball in the downward direction, and we also have the force of the string on the ball, and that's obviously in the upward direction. Now, at this point in the past several days, we've been saying that these two forces must be equal amounts, but in opposite directions. Because you have said in the past that since there is no acceleration here, you have said before then that this is a balanced situation. So we have balanced forces here with the ball hanging from a string from a rigid support. So with all that being said, we have to figure out what a summation even is. Now, in class, we talked about this symbol here being a Greek letter, sigma. And again, this should be in your book somewhere. And when you see that in front of an F standing for force, we're talking about the sum of all of the forces on an object. So in this case, what does that look like? Well, we have two forces here. We have the force of string on the ball, and we have a force of gravity on the ball. So we will simply add those together. That is the sum. Force of string, we'll just abbreviate with S, force of string on ball, and force of gravity on ball. That is our summation. Now the next question is, what is that summation equal to? Well, since this is balanced forces with no acceleration, we've also said this before, that if indeed this force of gravity on the ball is equal to the same amount as this force of string on ball in the opposite direction, we have said before that these forces must add up to 0. So we'll say that balanced forces sum to 0. Balanced forces sum to 0. Now, what does that mean and what does that do for us? Well, again, this is telling us that these two forces, when added together, essentially cancel each other out, and we get no force total zero force. So, something else I was going to add to that, and I didn't even think about it. Because this is in the vertical direction here, I'm going to go ahead and label this summation that we're doing as a summation in the y direction. So again, the y representing vertical. So this is a vertical situation here. And so all of our forces that we're adding are in the vertical, up and down here. So force of string plus force of gravity equals 0. Now, let's take a step back from what we did the other day with the gravity lab. How much force of gravity is there on this object? Well, we know there is a mass of 5 kilograms. That's the mass. And we know that the gravitational field strength is 10 newtons for every kilogram. So we can do some math here and figure out how much force of gravity we have on the ball. So this is what that will look like. Force of gravity equals 10 newtons for every kilogram times the mass of 5 kilograms, which gives us 50. Now look at the units here. That kilogram cancels that kilogram, and we end up with Newton then. That is our unit. 15 newtons is the gravity force. So, at this point now in our summation, we know what the gravity force is. We know that the gravity force plus the force of string is equal to 0. Now, one other thing about this gravity force is when you look at the force diagram, you have to ask yourself, well, what direction is this? And this is the downward direction. Because that's down, and because we're talking about y forces, that is forces in the y direction, downward typically is negative on the y-axis, and up we would normally think of as positive on the y-axis. So I'm going to add something here to this, a negative here, because I'm going to say that down is negative and up is positive according to our diagram. Now if I take that value over to my summation, here's what that will look like. So I have the summation of forces in the y direction equals force of string plus a negative 50 newtons equals 0. Which means if I solve this summation for the force of string on the ball, I simply add this negative 50 to both sides, I subtract the negative 50 from both sides, which means I add it. Let me do a little erasing here. So I add 50 newtons to both sides. And therefore, the force of string is positive 50 newtons. So you think about that. We have gravity pulling down with what we would consider a negative 50 newtons. We have the string pulling up with what we would consider a positive 50 newtons. And obviously, positive 50 plus a negative 50 equals 0, which again reinforces the fact that we have balanced forces here. So hopefully that even though it's kind of a mess, makes a little bit of sense for you. Now, the next question we have to answer is, what happens if the forces are not balanced? How do we handle that situation? Well, let's take a look here. So when the forces are not balanced, what do they sum to? Well, just the generic expression you would see. Well, hold on here. Scratch that. So, unbalanced forces are what we're talking about now. And so, with unbalanced forces, a sum, I tell you, I'm not making very good sigmas. Let's try that again. A little better. So, the sum of all forces, if a scenario is unbalanced, equals m times a. And again, we found this out with the ping pong ball lab. So this right here is what the summation of all forces equals when we have unbalanced forces. When you have balanced forces, you don't have an acceleration. And so if A is 0, then your sum of your forces equals 0 on this side, if A is 0. If A is not 0, like when you have unbalanced forces, then we do have a number here. We have an actual value that the sum of all the forces is equal to. Now, what is that exactly going to look like? Well, I have another little scenario here we can take a look at and hopefully make some sense of it. Okay, so in this situation, we clearly have an object that is experiencing unbalanced forces. At least it should be clear. We have a tension force on this side, so some kind of string or rope or cable that's pulling with 25 newtons of force. On the opposing side, we have a friction force, and again, this friction force is opposing the motion of the object, and that's a 10 Newton force. So what I'd like to start with at least is just drawing a force diagram for this object here. And so what is that exactly going to look like? Well, again, we start with our dot because we circle our system, and our system is the actual block. So all the forces, we want to draw in and label all of the forces acting on this object. And so we have a force acting in the downward direction, and again, it's force of gravity on, I'll just call it a box. We also have whatever this box is sitting on, some surface. Maybe it's the floor, so maybe I'll say it's the force of floor on box. So those are the two forces we have so far, and again, those aren't even labeled in our picture. But we know that the force of gravity is on all objects, and if this object is sitting on a surface, there must also be a force of the surface back up in the opposite direction of gravity on the object. So now we have the two forces that are actually in the picture that we need to account for, and so we have a force of, I don't know, we could call it force of cable or rope, force of rope on box, pulling to the right. And to the left, we have a shorter arrow. Notice the arrow is shorter. And we have that arrow to the left. And again, that would be the force of friction on box. So this is our force diagram with all four forces drawn in. Now, this summation idea. What exactly do we do? How do we go from here? Well, and here's where it gets a little more complicated than the last example. So now we have forces that are going up and down. We also have forces that are going left and right. We need to account for those and do summations separately. Just like in the last scenario, I had mentioned that since it was all vertical, we were calling that a summation in the y direction. We'll do that, but we'll also have a summation in the x direction because the x direction forces have to be accounted for separately from the y direction forces. So what is all that going to look like? Well, let's see. First of all, using what we said before, knowing that the force of gravity on an object is equal to 10 newtons for every kilogram times its mass, we can do that in this case and figure out how much force the gravity force is. So, in this case, we have 10 newtons for every kilogram. And I apologize, this is getting a little messy here. And we have a mass of 3 kilograms, as you see written on the block. And so 10 newtons per kilogram times 3 kilograms, the unit kilogram cancels, and we have 30, so 10 newtons times 3, 30 newtons of gravity force. And again, I'm going to label that as a negative because that force is in the downward direction. And down is going to be negative, up is going to be positive. In the same way, with x direction, we have typically to the right as being positive and to the left as being negative, if we think of it in terms of the typical xy coordinate system. Now, knowing that our gravity force is a negative 30, that tells us that this is negative 30, that the force of the floor on the box must be a positive 30, because we know that any object sitting on a surface like this that is not accelerating up or down is experiencing balanced forces. And so we would have the summation equal to 0 here in the y direction. So sum of the forces in the y direction equals the gravity force, which again, we just found that gravity force is negative 30 newtons. So negative, hold on, I'm getting ahead of myself. Let me actually write the symbols out here. So force of gravity plus force of floor, and that's all going to equal 0. Now that means that the force of floor is going to be positive 30, which is the opposite direction, but the same value as the gravity force. So again, just to kind of show you this negative 30 newtons of the gravity force plus the 30 newtons of the floor pushing up gives us this summation equal to 0. Now, that's for the y, which is just repeating what we did in the last example. The x direction is the stuff that's a little different than what we had done before. So now we have the forces sum in the x direction, and again, we just need to write the names down. We have the force of the rope on the box and the force of friction on the box. So I'm going to write those in here. We have force of rope plus force of friction. And that is going to not equal 0. That is a non-zero summation because as you see in the picture, this force is longer than this force in our arrows. We see values here. We have 25 newtons here. We have only 10 newtons here. And that is going to equal, the sum is going to equal ma, or mass times acceleration. Now, what we can begin doing is start putting in our numbers here. Do we know what the force of the rope is? That'd be the tension force here. Again, the rope force on the box. Well, it tells us it's 25 newtons, and that is in the right direction. So to the right, 25 newtons. So that is a positive 25 newtons. So we'll write that in there, 25 newtons positive for the force of the rope. Plus, now we look at the friction force. Well, the friction force is 10 newtons, but it's to the left. And if the right is positive, then the left has to be negative. So that 10 newtons here is actually a negative 10 newtons in our summation. Negative 10 newtons because of the direction. And what does that equal? Well, it equals mass times acceleration. Now, I don't want to bother with this quite yet. First, let's figure out what this here is. So the summation on the left side of the equation here, what does that give us? 25 newtons plus a negative 10 newtons gives us a 15. That'd be a positive 15 newtons. And that equals, again, mass times acceleration. So that means for this little box here, sitting on whatever this surface is, the floor, being pulled by some rope, being opposed by friction, the total sum of all the forces on this object is 15 newtons in the positive x direction. That'd be to the right. So 15 newtons to the right is the sum of all the forces on this box. And that equals m times a. Now, what is the m? Well, the mass is 3 kilograms. So if I want to know how quickly this object will accelerate, all I have to know is how massive the object is. So I can continue on here, and I can put the mass of 3 kilograms in for mass, and I still don't know the acceleration. But I can easily find it by dividing both sides by 3 kilograms, which gives me A then by itself, as these cancel. And I'll have to rewrite this over here to the side. So A then equals 5 is the value. Now notice, this is newtons for every or per kilogram. Well, this does not sound like an acceleration unit that we had before. So what exactly does that mean? Well, a newton for every kilogram is the same thing as a meter per second for every second. So the same unit that we were using for acceleration before is this newton for every kilogram that we see now. So in this case, our acceleration then is 5 meters per second for every second, meaning that this box here is going to get faster by 5 meters per second every second that it's being pulled by this 25 Newton force from the rope. So I hope, even though this went a little long here, hopefully this made sense to you. If not, watch it back and see if there's some things you missed. I'm sure we'll be talking about more of this in class. So again, hope it helped a little bit at least.